Good evening, everyone. Welcome back to our YouTube channel. Well, today we're going to take you through how far we've gone. We've been able to, because we've been going through the data analysis, we came up with the idea, we've moved a step, and this time around we were able to try to come up with models that we could test and then put them in, like see how best they could work in the real world. Well, it's me, Manjuna Chirija, again, together with Tahai Seiji, and we're going to take you through the conservational graph retrieval fine-tuning model for elementary education. And our contents are going to be based, we're going to have the introduction. Yes, we're going to take you through the introduction. We're going to take you through the related works. We're going to take you through the problem statements. There are questions that we asked ourselves when we're carrying out research, the objectives we came up. We're going to take you through the contributions and then the methodology, the dataset description, results, conclusions, limitations, and the rest. So we're going to start from the background and introduction. Well, for the background and introduction, when we look at adaptive learning delivers education that utilizes the technology. And from back then, they have been trying to come up with things that will actually help students learn at their different places, because the problem that we're focusing on here is that children tend to learn they learn at different places. So what you're looking at here is making sure that what we come up with is actually going to solve that. And we are basing on 4 techniques that we looked at: RAFT, which helps to enhance to retrieve data from the external databases, as we've been talking about it previously. Then the GPTs that are designed to understand and generate human-like text. And then we have the NLP and NLU, which helps us to understand the student's input and generate the human language. Yes, because we've seen that in the RAF there is a fine-tuning, and then you get the data from the external databases, then you have to adjust it so that it fits in. Yes. Then of course, having been given you an introduction, there are very many people who have actually done this, people who have tried to do this so that it actually brings up something. And this comes in under related works. And we say that recommendation has a challenge of one size fits all, because when they're recommending something, sometimes they think that it fits for everyone. But they have tried to work on this in the entertainment sector and also in the shopping sector. For example, Netflix and Amazon tends to give you what actually fits in what you like. Yes. And for the education sector, it's all still lagging behind. But a few examples that we have that have tried to incorporate it, we have Khan Academy, Duolingo, and a system, an adaptive learning engine that is called eGotsky. So for this engine that I'm going to talk about, it was brought up to help students learn. Okay, it was brought up so that they could help elementary children, and it was tested on hundreds of students so that they could learn fractions in 5 months. And they used it for 5 months, and they actually got to realize that the results that came out, 17% of the time was reduced, so that children could actually master and know what they're actually doing. So this actually gave a good chance of, yes, this could actually work, and it's actually giving a very good impact. But the problem that is faced by the works nowadays is that there is, most of the systems work on predefined rules. Like maybe the person, let me say how they can be like, if this person does this and this and this and they fail it, then give them this. So those rules are set, they're standard. The model doesn't get time to think for itself and recommend something. And the solution that we actually look through when we get to read through the different things, the solution that comes in is that when you get to use GPT models, the GPT models, they also incorporate natural language processing and natural language understanding. They understand what the student is actually saying and give recommendations that are not predefined, but rather they are brought up from the context of the student, the different students. Yeah. And our problem statement, as we've said, it's a problem of one size fits all approach that is normally said in the element. And this is mainly for us, we're going to mainly focus on the elementary section, because this is the foundation of everyone's education. You start small and come big to wherever you are. So when we start fixing the issue from down, the child gets to learn better on how to adopt, and the paces are followed so they can recommend good stuff for them. Yeah, and with this, it increases their learning capabilities. But when you're coming up with a system, you always face challenges, as we've always been telling you that there are challenges that we expect to face in this. For example, imbalanced data sets, and then we can face that problem of overfitting and underfitting, data drift and concept drift, model interpretability, where we talk about it being a black box, then scalability issues where the numbers are growing, but it's not being able to cater for all those big numbers. Then we talk about scalability issues. We've talked about scalability issues. We talk about the cold start problem, where it doesn't have enough, like you are a new user, so it doesn't know how best it should recommend for you since you're a first-time user. Then real-time processing requirements, where they need feedback at that very moment. Then few short and zero short learning challenges, where it has little content to start from or completely nothing. Then also the ethics, whereby it's hard for them to know how can we trust this, or maybe it has come up with a decision that affects the students' outcomes and all. Well, when we're carrying out this research, the research about different things, because when you're coming up with something, you first find out what's actually happening in the world. So we asked ourselves a few questions. We asked ourselves, how can a generative model dynamically adjust this content? Because it's hard to say that something is actually going to recommend this for you, do this for you, do this for you. So how can we make sure that that generative model can dynamically adjust that content based on difficulty, based on your performance and the learning behavior? We asked ourselves how the techniques that we have chosen to use can enhance the student engagement, and what machine learning techniques are most efficient in analyzing the student interactions so that it can provide continuous learning optimization. And with this, we came up with objectives that we're going to design a generative model that personalizes the learning experiences, that enhances student engagement and motivation through interactive experiences, and then to ensure that the platform relies on dynamic content, not static content, and also to neglect the biases for training the data that normally leads to unfair personalization. Yeah, and the contributions that have come out of this is that we've been able to develop a model that can enhance personalized mathematical learning using the retrieval RAG, that's retrieval augmented generation. Then we've implemented an adaptive learning framework. We've leveraged a transformer-based model. We've designed a scalable and efficient system, and we hope to be exposed to new research opportunities. Yes, and the methodology that has been going through, as for those who have been following us from the beginning, we had to look for the data sets. So we had the data sets, then we had to process them. In that processing, we had to find out their missing data. That's the EDA analysis and all that. Then we had to go to feature engineering, where we had to look for what do we need, what don't we need. Then from that, we come up with a model, like model development and stuff. Then we select the model. When you select the model, the models you're going to come up with, you train. After training it, then we evaluate the work. Then after evaluating it, if you feel like that the performance is acceptable, then you move on and deploy it and then monitor and maintain it. But if you read the acceptance performance and you feel like it's not good, maybe the performance, the accuracy getting is in negatives, you go back to the step of feature engineering and start afresh. Yes. So I'm going to hand over to my partner to take you through the parts that are remaining. Yes, thank you.
Hello everyone. My name is Eugene Twice, and I'm going to take you through the outputs and the expected results and the discussion related to how our model training was and how we train. So first of all, we're using a GPT. We're trying to use a GPT transformer to create a model that helps us create a generative text so that when you ask a question mathematically, based on mathematical word problems, which are based on mathematics, like addition, subtraction, multiplication, or division, it's supposed to give you an expected result with maybe an explanation, or depending on how the model is. So we were able to collect some results from the model training, and this is how we were able to visualize them. So the first model that we have here is what we call the TSNE embedding visualization model. So this one helps us to create a 2D representation of the high dimensional embeddings for this model. So basically, what happens is it helps us visualize the different questions that we have and cluster them together. So if we have, for example, clusters, as you can see here, it represents that is how the model is understanding the relationship between various questions based on the various parameters in our data set or in the model. Then we have a feature importance via attention weights heat map. So basically what this does is it relates based on the tokens. For example, in this case, we are using a question, what is 5 plus 7? So it will relate based on the word and first tokenize each word in the sentence, and then it will be able to relate the importance based on this heat map. So as you can see, red means it's the most important, and blue means it is least important, relating to what is the correlation between each word to each other. So the next graph we have is what we call a token length graph. So a token length graph helps us create visualize token distribution between frequently different words or tokens that appear in the dataset. So it helps us understand the bias between data and model tokenization. Then we have a graph that evaluates the training loss against the evaluation loss. So as we can see, this training loss keeps decreasing as the number of epochs increase. In our model, to save computational power and time, we decided to use 20 epochs for our initial model run. So as you can see, the training loss keeps decreasing. So decreasing the loss helps to show us that the model is trying, as the epochs increase, the loss keeps reducing. So this helps us show that the model is actually training, and it is trying to close the window within which the loss is happening during the training process. Then the evaluation helps, as you can see, as the epochs increase, the evaluations increase gradually. So, however, in our case, as when the evaluation loss is high and the training loss is low, it creates a situation of overfitting. So this creates a situation of overfitting. Then we have a learning rate curve, whereby from our model, when we run it, we're able to obtain the learning rate based on the number of epochs we had. So as you can see, the learning rate keeps decreasing as the number of epochs increase. So this one shows that the learning rate, meaning the number, the time taken or the weights that are used keep reducing as time goes on and as the number of epochs keep increasing. Then we have what we call a FIS index. So FIS in full is a Facebook AI search and search algorithm. So this index helps us to create similarity between the questions, or in our case, between questions and queries. So in this case, we put in a question like what is 2 plus 2? Then it will give us 3 similar questions and show us their similarity indices. So this shows that the closer it is to 1, the more similar it is to that number, and it gives us the top 3 most similar questions from our data set. Then we have a confusion matrix that helps us predict based on the series of questions that we have. So for example, we put in 4 sample questions from our data set, and we have what we call the true label and the predicted label. So from what we gathered, we found that the only time we were able to get total predictions is when they were truly incorrect questions giving us predicted correct questions. That's what nearly all our results were showing. None of them were giving us the rest of the other field values. Then lastly, we have a table of the total training statistics that we have. So as you can see here, we have the epochs and the evaluation accuracy, the grad norm, and the learning rate, the loss, the step, and evaluation loss, and the variant time. So the epochs which are in decimal points, which are not entirely 1 or 2, these are like mini epochs that range from 0.1484 up to 0.8902 up to 1. So these ones help us to give us a evaluation accuracies. They started from around 0.904. Then, of course, I'm showing you the sample up to the 18th epoch, which goes up to 2.37 and following. Yeah. So in conclusion, we have seen that this work that we have been doing, it integrates conversational graph retrieval augmented fine-tuning, and we needed to enhance the math problem solving in elementary education, because since we are training with transformers, we have to combine knowledge graphs with the transformers. So it will help to increase accuracy and better contextual understanding. However, we had a few challenges, like training times were long. Usually you're training a model for like hours or even days, and yet you're getting no results or no even accuracy of 0. So you have to keep doing it over. Hence, we are able to only create only one model as of now. Then model scalability issues. Usually, if you are committing to GitHub, you find that the models are too heavy. So you can only scale the interface or maybe the code that helps run the model, but the model itself, it can't be scalable. Then also it was also the same problem in our deployment and also efficiency. So when you're writing, like creating to simulate a problem solver with a question, to give you just a scrambled text, which is not even correlated with the question. Then the limitations we had in this project was the high computational requirements. So because of our devices, we had limited GPU resources that were able to run this model. And even if you go to online, most of these online services like Cargo, Colab, or even Amazon page to store our model. For example, Cargo gives us maximum of 20 GB storage, yet we had a model which was like around 25 GB. So it will just stop running the model midway and we would just discard the rest. Then hyperparameter sensitivity. So getting the correct learning rate, the batch size, even the dropout values, it needed a lot of fine tuning, and it was slowing our progress. So it was slowing our progress very much. So we find that we are running, but after 2 days of running the model, we find you're still getting the same values of no accuracy, no precision. Then graph size scalability issues. Larger knowledge graphs increase the retrieval time, making the real-time processing really challenging. Then when it came to the data limitations, graph retrieval was not effective on our side because it needed the quality of the knowledge graph which we were supposed to get from our model. So from our data set, which was a bit limited, we will find that it lacked key relationships. So the graph performance or the retrieval performance dropped very highly. Then data processing, cleaning this data set, which required both text and numerical data, we had to try to fit it with the graph-based retrieval models. It took a lot of time, and it had the highly effectiveness and even applicability in the real world, then we'll have to optimize retrieval process by refining the file indexing and reduce query latency. Then we have to expand the dataset to include even more complex concepts in mathematics that will help to generalize the different levels of this education, the elementary level. Then implementing lightweight development strategies like ONNX, which will help the model to run efficiently on low resource devices. So for now, we are using Streamlit to deploy our model. However, it's not very capable to run on low resource devices. Then integrating active learning, we shall need to integrate active learning to enable the system to improve by learners' user interactions while incorporating explainability in the explanations and the solutions that it gives. And finally, developing an interactive web mobile platform that is going to make it AI-driven in the education sector, that's going to make it more user-friendly and in the future, highly and widely accessible. Thank you very much. That is all I could say.